A very good morning, everyone, and thank you so much, Keith, for a nice introduction. And I'm also very thankful to the organizers for having me here. It's truly an honor and pleasure to attend this conference for the first time, and really learning a lot from all of you. So today I'm going to talk about MISPR, which is an open source computational framework developed by our lab for simulating electrolytes, and also we try to do interfaces. And here is an overview. I would like to give you a brief overview of MISPR, some of the key features. I will demonstrate some of the automated workflows we have in MISPR, and then we'll show you the computational spectroscopic analysis tool in MISPR and how we are using it to design optimal electrolytes for battery applications. So as you know, over the last few decades, there is a paradigm shift in how materials are discovered and designed using a data-driven approach. And by definition, any data-driven approach starts with data. So a large component here is integration of large-scale data, which can come either using high-throughput experimentation. In our case, we are trying to generate this large data using high-throughput multi-scale simulations. And I'm sure one thing that we can all agree on that these simulations are still pretty expensive and time-consuming. So another thrust in our lab is focused on using large language model to extract existing electrochemistry information from literature. However, I won't talk about this area today. And while these first two pillars gives us the information about the materials and their corresponding property, we need to simultaneously advance computational spectroscopy analysis tool to basically understand the atomistic interactions which governs the structure-property relationship. So that's another area where we are working on. And finally, combining all this information to develop machine learning models to predict properties of electrolytes. We are also focusing on developing open source computational databases and collaborative platforms which a broad community can use. All right, so as many of you know, many groups in the scientific community leverage the advances in theory and advancement in computational resources to accelerate materials discovery by developing computational infrastructure and large-scale databases. Some of the very well-known examples are Materials Project, OQMD, Jarvis, which came out from NIST, to name a few, and there are many, many more. However, most of these computational infrastructures are primarily focused on solid-state materials or nanoporous materials, and compared to solids, much less attention was given to liquids. So for liquids, electrolyte genome was one of the early examples where we implemented high-throughput DFT calculations to screen electrolytes based on their electronic properties. However, as we know, when we're talking about liquids, just DFT calculations are not enough, and we need to also look into the structural evolution of the electrolytes and their transport properties. So we need to implement these high-throughput techniques both at the quantum as well as at the classical level. So to overcome that challenge, we developed MISPR, which stands for Materials Informatics for Structure Property Relationships. It's an open source, high throughput, multi-scale infrastructure for materials design, and we tried to make it as generic as possible. We start with an initial database of molecular components, so let's say thousands of solvents we want to explore for any given application. And as a first step, we perform high throughput DFT calculations. We have several automated workflows to do that, and I'll show you an example of some of the workflows in MISPR. We then generate the force field parameters, which are then used to perform classical MD simulations in a high throughput manner. In this feedback loop, we then extract hundreds and thousands of molecular clusters from MD simulations, categorize them based on their solvation environment, and feed it back to DFT. And throughout the process, we are building databases of properties computed from DFT and MD simulations, which are then used to train machine learning models. So MISPR can be used for high-throughput screening, where we can start with a very large pool of candidates and systematically down-select them based on property evaluation. And it also helps us in establishing structure-property relationships by exploring a very wide and broad chemical and parameter space. So one of the example of the simplest workflow in MISPR is for calculation of binding energy. I'm sure many of you would have done it already. It's a critical property to understand the stability of bond between any two species. So all the workflows in MISPR look very similar, that the bare minimal input requires is just the structure of your molecular component, or it could be a SMILE string, whatever your favorite format is. And it will perform automatically the geometry optimization and frequency for two species. It can be two molecular component or a molecule or a solid. It then binds the two complexes binds the two species based on the binding site provided by the user, calculates the binding energy, and store it in a database. We have been exploiting binding energy for a lot of different applications, and this is an example where we use the workflow to identify different functional groups that can be attached to graphene to strongly bind some of the lithium polysulfide species in lithium sulfur batteries, and further use that information for modeling the lithium sulfur battery interfaces. All right, another example of a DFT implemented workflow is for calculation of redox potential. And people who are working on energy storage area would appreciate that this is a very critical property for identifying electrolytes with high electrochemical stability window. And if you have done this calculation, you would know that there are many flavors of different models of theory. You can do a simple homo-lumo calculation, a gas phase calculation like one we saw in the previous talk, or you can actually calculate an entire thermodynamic cycle with the calculation in gas phase and in solvation phase. So another variation is when you have a proton donor present in the solution, such as in case of aqueous electrolyte. And then you have to calculate this proton-coupled electron transfer process. So the workflow is quite flexible with a tree-like structure when the user can do a single electron or n electron calculation in gas phase or in solvation phase, and you get the corresponding output. And in case of aqueous electrolyte, and this is an example for a redox active molecule canoxylene, where we basically computed the SPCET process, and this is the corresponding electron transfer diagram for first and second electron potential as a function of pH. So again, the workflow is quite flexible depending on whatever level of theory you want to pick, and it will give you the corresponding output. The last example of DFT-based workflow I want to show is for calculation of bond dissociation energy, which is another very critical property for estimating the stability of the bond. And this can be used actually as a first metric to determine which species are likely going to break at the interface and can contribute to the formation of inner layer of solid electrolyte interface. And generally these calculations are very, requires a lot of effort because for the reactant and all possible products, we need to optimize the structure and then Hessian is computed. So it's very intensive calculation. So using the workflow, the only thing we need to provide is the input structure of the molecule. It takes care of the rest of the things. It optimizes the structure, do the break. By default, it breaks all bonds, but we can choose which bonds we want to break, and then for all fragments, do the calculations again. And you can see a visual output where we can see which bonds are most likely to break at a certain condition. And we can do this for a single molecule, for solvation structure extracted from, let's say, MD simulation, where we know if we are forming ion pairs or if we have, let's say, solvent around the cation. So this is how the roadmap of workflows, current roadmap of workflows looks in MISPR. We have several fully automated DFT-based workflows for calculating of, let's say, electrostatic partial charges, NMR chemical shift, binding energy, bond dissociation energy, and redox potential. And we are currently working on developing similar workflows for Raman and IR spectra as well. The MD workflows take care of everything from just providing the molecular structure, getting the charges, getting the force field, running the MD simulations, parsing back the output files, storing everything in a database, and doing the analysis. For analysis, we have our own standalone code base called MD-Prop tool, which have several routines for commonly used structural and transport property analysis. And then we have the hybrid workflows, which starts from DFT, do MD simulations, do molecular cluster extraction from MD simulations, and then go back to DFT. An example of a hybrid workflow is for calculation of nuclear magnetic resonance chemical shift using explicit-implicit solvation model, and I'll talk about this particular hybrid workflow in detail. So we have three types of databases currently in MISPR. The database is computed from DFT properties, the force field ones, and the ones getting from MD properties. And every property is stored in its own respective collection. And along with the data itself and the properties information itself, we also store a lot of metadata like molecule, software information, time required to do these calculations, which is very important for transparency in data sharing and reproducibility of the results. All right, so MISPR allows us to build large-scale databases of electrolyte properties. At the back end, we are using MongoDB database. It's built upon several existing very powerful libraries in the material science community. So we are using PyMedGen for molecule representation, Fireworks for workflow management, and for managing supercomputing resources. We developed our own custodian package, extended version for Gaussian, where basically if it acts as like an on-the-fly error handler. So if we're running thousands of calculations and let's say 10% fail, it automatically fixes those error, which the ones we know how to fix, and then reduces manual interference and allows more automated calculations of systems. The unique feature of MISPR includes this seamless integration of DFT and MD simulations, and it comes with a lot of post-processing analysis toolkit. We tried to make it a well-documented website. I'll give you a short demo of this during the end of the talk, but the source code is available here, and here is the website. And again, the installation is pretty simple with using the pip install MISPR. Okay, so let's dig deep a little bit into the scientific understanding of electrolyte systems, and I'm sure everyone can appreciate here that solvation structure is one of the key ingredient in understanding and predicting the properties of electrolytes, and it's the intimate dance of the solvents around the solute which control the chemical and physical properties. And in the electrolytes, just with the basic three ingredients, a cation, anion, and a solvent, sometimes we have binary solvents and additives. It's not always trivial to predict the solvation structure because minor changes in the molecular features can lead to significant changes in the solvation structure, and these properties are non-additive in nature. Also, it's very important to understand solvation structures, for example, in battery application or electrochemistry application, but because it drives a lot of transport and mechanical properties. So experimentally, the most commonly used techniques for characterizing the solvation structure are NMR, spectra, Raman, X-ray pair distribution, SCXRD. Among these techniques, one of the most powerful and widely used technique is NMR because it gives you a lot of detail about the conformational dynamics and connectivity of the molecular structure. But NMR comes with its own limitation. They are limited by the temporal resolution and the low sensitivity, and which makes it difficult to deconvolute this experimental spectrum and assign it to a particular solvation structure. So oftentimes, this spectroscopic fingerprinting, which means mapping these peaks to a particular solvation structure, is done using quantum chemistry calculations, either DFT or AIMD simulations, and the simulations have their own challenges. So traditionally, how these calculations or mapping is done is we get the experimental spectrum using DFT or AIMD simulations. We try to come up with the solvation structure which matches with the pointer is not working, which matches with the center of the experimental peak. Okay? And this overall approach is fraught with bias and a lot of manual intervention because we try to come up with the structures that matching with the center of this experimental spectrum and leave aside many possible configuration in the solution. Also, because of the high computational cost of DFT and AIMD simulation, we end up inaccurately accounting the solvation effect and focus on this single structure, which again which we believe can represent the entire liquid solution. Okay, I think it's out of battery. So we're talking about batteries and it's out of batteries.
That's why you need to improve them.
Yeah. All right. So the computational spectroscopic analysis tool in MISPR starts with as simple as just providing the molecular structure. So you just provide the structure of the cation, anion, and solvent, or like I said, SMILES, NCHI, whatever your favorite format is. It will run an ESP workflow, which will do all the DFT calculations, get the charges, get the force field parameters. Currently, we have support for GAF and OPLS, but the user can provide whatever force field parameters you want. It will then run the MD simulations, and here the user can supply the concentration, temperature, their own force field parameters. Based on the structural analysis for MD simulations, we then extract hundreds and thousands of molecular clusters and then categorize them based on their solvation environment. And these top clusters are then subjected to the NMR workflow, where we again do the DFT calculations to calculate the NMR chemical shifts. And all these information is stored in a MongoDB database for easy retrieval and analysis and direct comparison with the experimental spectrum. All right, so I'll show you an example where we use the workflow to resolve the discrepancy of the solvation structure of this electrolyte, magnesium TFSI and DME solvent. It's a very well-studied electrolyte because it gives a lot of good properties in magnesium and batteries. So some of the previously reported SCXRD experiments suggest that we are forming solvent-separated ion pairs in the solution, whereas some of the previous simulations suggest that we are forming ion pairs in the solution. And when you're talking about batteries, again, there's a lot of work that, and I think in the next talk you will also see how changes with concentration lead to different type of solvation environment, and that play a very important role in controlling the transport properties of electrolytes. So it's very important to differentiate if we are forming solvent-separated ion pairs or contact ion pairs or aggregates in the solution. So using the workflow, we basically, the workflow that I just showed you before, we calculated the NMR chemical shift for this electrolyte. So the black curve here is the experimental spectrum, and the colored bar are the computationally predicted NMR chemical shifts. So the top structure here is where we are forming solvent-separated ion pairs, and the predicted chemical shifts matches exactly with the center of the experimental spectrum. So great, we were able to identify this most stable structure which has the probability of occurrence of more than 80%, and it's the same structure which was previously reported by the SCXRD experiments. But an advantage of the workflow is that it's because there's no manual interference or chemical intuition, we are not only focusing on this one structure which matches with the center of the spectra, but also the other stable and metastable structure in the solution. So the broad line half width of this NMR spectra actually tells us that we do have multiple stable structure present in the solution, and then there is a rapid exchange in the solvation environment, but it's nearly impossible to get all those structures using experiments alone or even using manual intuition and DFT calculations. So using the workflow, we identified 5 other stable structures which are present in the solution and control the transport properties of this electrolyte. We also spent a lot of time. These NMR chemical shifts are very, very sensitive to the different configurations. So we were having a lot of trouble actually. We were having a lot of discrepancies in matching with the experimental data. So we spent a lot of time in finding the culprits which affects the accuracy of these NMR chemical shift calculations. We know the main culprits are, of course, the force field parameters we used in MD calculations and the DFT level of theory. Other than that, the solvation model, how we sample the conformers, whether or not we do the geometry optimization for the clusters extracted from MD simulations. All these factors play a very important role in calculating the NMR chemical shifts. So of course, the quality of any MD simulation depends on the force field parameters. So we tested the commonly used force field for this electrolyte in the literature, and these are all atom MD calculations. So we tested GAF, OPLS, and polarizable OPLS force field. So looking at the RDF here, you're looking at cation solvent and cation anion RDF. And you will see that GAF predicts that we have a very weak cation solvent interaction and a very strong cation anion interaction. Contrary to that, polarizable OPLS force field suggests almost a negligible cation anion interaction and a very strong cation solvent interaction, which can also be seen here in the coordination number analysis. So if I use GAF, it tells me I'm forming aggregates. If I use OPLS, it tells me I'm forming contact ion pairs. If I use polarizable OPLS force field, it tells me I'm forming solvent-separated ion pairs. And that could be one of the reasons why experimentalists don't believe computational people sometimes, because right now, depending on whatever force field I choose, I can predict any type of solvation structure. So we further dig deep into kind of different, again, run the entire workflow to extract all possible configurations with these 3 different force fields. Overall, we found that GAF and OPLS gives over prediction of the cation and ion coordination and a more heterogeneous distribution of configurations. Compared to that, polarizable OPLS force field gives a more homogeneous distribution with like more strong interaction between cation and solvent. Okay. So based on the experimental results in our work and the previously reported experimental data, our conclusion was that for this particular electrolyte, the polarizable OPLS force field gives the most accurate structural properties. Okay. And the second culprit, as we know, is the DFT level of theory, right? So we performed extensive benchmarking on different functionals and basis sets, and here I'm showing you the benchmarking for magnesium NMR chemical shifts, but we did a similar benchmarking for carbon and proton chemical shift as well. So on the left corner, you can see going from top to bottom, again, depending on the functional, the accuracy varies for the prediction of NMR chemical shifts. Going from left to right, the accuracy improves as we increase the basis set, right? So we had 3 criteria to choose the level of theory. We wanted it to be, of course, accurate. We were also concerned about the computational cost and tendency for these calculations to fail. So based on those 3 criteria, we chose the MO6 and omega B97X, which gives the most accurate prediction for magnesium NMR chemical shift. The result varies a little bit for proton and carbon NMR chemical shifts. All right, so overall, based on this, the recipe that we cooked up, the methodology and the benchmarking we did, we applied this workflow for a variety of different electrolyte battery applications, including magnesium, lithium-ion batteries, sodium-ion batteries, and even to some complex biomolecules. And it does a pretty good job so far in predicting the multiple stable structure present in the solution. There are definitely discrepancies which we are currently working on, because we are talking about 2 different time scales. The NMR gives you an average over microsecond, and MD gives you a time scale of a nanosecond. We, of course, don't want to run very expensive calculations as well. So we are trying to resolve that with vectors by incorporating residence time and formation energy, and taking into account when we are extracting the cluster. But that's and also right now we only looked at the first solvation shell, which works pretty well for the concentration and temperature ranges that we are considering. If we go for highly concentrated electrolyte or ionic liquids, where we have to worry about long range interactions, second solvation shell, that adds additional computational cost, which we have not considered. With that being said, the workflow is extremely flexible. If somebody wants to use and go for a second solvation shell or more expensive calculations, they can do that by all means. So overall, the workflow significantly reduces the time and effort required to do these calculations. And this is an example where we ran 300 carbon and 600 proton NMR chemical shifts. And these are for single molecule calculations, not mixtures, for almost 100 molecules in less than 24 hours at the benchmark theory level. And you can see that the predicted chemical shifts are in excellent agreement with the experimental chemical shifts. Okay. This is an example of the NMR document. I just wanted to show one example, and all other documents in the database look very similar, where we save all the information about the molecular structure, of course, the calculation results, the level of theory we are using, and along with all the metadata, which is, again, as I said, is very important for transparency in data sharing and reproducibility of the data. All right, in the next half of this talk, I want to show you an example of how we are using MISPR to design optimal electrolytes for battery applications. I'm sure most of you are familiar with lithium-ion battery. Has anyone heard about lithium-sulfur batteries? Yes, right, many of you, right? So lithium-sulfur batteries, for those of you who don't know, is one of the most potential candidates to replace lithium-ion batteries in the future, because of their ability to provide almost 5 times higher energy density at a significantly lower cost. And these batteries are not new. The research pretty much started at the same time or a little bit late than lithium-ion batteries. So it's 5-decade-old research. And these lithium-sulfur batteries still suffer from low charging efficiency and poor safety. Unlike lithium-ion batteries or magnesium-ion batteries, where we have the intercalation chemistry, where the problems often originates from the electrode itself and things that happen at the interface. In this chemical transformation chemistry, the problem often originates from the electrolytes. So what happens in lithium sulfur batteries is during the discharge process, when lithium reacts with sulfur, it forms a bunch of different lithium polysulfide species which migrate toward the lithium metal anode side and result in parasitic reaction. So most of the effort in literature is focused on somehow blocking these lithium polysulfide species toward the cathode side, either using coatings, physical membranes, or modifying the cathode itself, which works to a certain extent but doesn't really solve the challenges we face in lithium sulfur batteries. So we decided to tune the solvation structure of lithium sulfur battery electrolytes and targeting 4 key properties. We wanted to suppress the solubility of these lithium polysulfide species while simultaneously increase the solubility of the salt, and we wanted to increase the ionic conductivity while suppressing the viscosity. So you can imagine all these properties move in a different direction. So like any other researcher, we digged into the literature and we found that in last 20 years, only 56 solvents have been tested experimentally for lithium sulfur batteries, and this spans 16 different chemical classes, include everything from ethers, azoles, sulfonamides. The requirement of lithium sulfur batteries are more complex than other battery chemistries again. So we often end up using a binary solvent mixture. The state-of-the-art solvent mixture is dioxylane, a 1:1 ratio mixture of dioxylane and dimethoxyethane, which is an ether solvent mixture. The state-of-the-art salt is 1 molar lithium TFSI, and an actual electrolyte in a battery during a discharge or charging process, once you start operating the battery, consists a bunch of different lithium polysulfide species, all the way from Li2S2, Li2S3 to Li2S8. So you can see it's a little bit more complex mixture than any other traditional electrolyte that we use. So what's the problem with this state-of-the-art electrolyte is that the DME solvent shows a preferential solvation for lithium cation, which results in very high solubility of these lithium polysulfide species, which is undesirable. So we decided to find a new buddy, a new co-solvent for DOL and replacing DME. And we started building these guiding maps based on binding energy. So binding energy of the solvent with lithium polysulfides and with the salt. And here we considered all possible chemical classes which have been tested in the literature. So those are the different markers. And the size of the markers actually correlates with the desolvation energy, which was computed using MD property. And we found that there's a good correlation between binding energy and desolvation energy in many cases. Overall, the binding energy depends strongly on the chemical classes of the solvents. So we have a lot of fluorinated solvents here, ethers line this area, we have sulfoxanes, sulfonamides. There are definitely a lot of outliers here. So some of the ethers like tetraglyme, they show very high binding affinity for both the salt as well as polysulfides. And on the other top extreme, we have solvents which belongs to the silane category. Okay, because we are trying to replace DME, anything which falls in this region can be a potential co-solvent because it can show low solubility for lithium polysulfides. I don't expect anyone to be able to read anything here, but just focus on the color scheme is where we did MD simulations for all the electrolytes which have been tested in the literature, different solvent classes, and it gives us similar information. And previously it was the DFT calculation. This is MD simulation, but what we noticed here, the red column is the bridging effect, the green one are the binding energies, and the purple ones are the probability of forming clusters of different sizes, from 1 being the smallest and 4 being the largest. they tells us the same thing, that fluorinated non-polar silane and sulfides are the solvent categories which results in very large cluster formation and can significantly suppress polysulfide solubility, which tells us that binding energy, which is a very cheap calculations, can be used as a potential descriptor for estimating in certain cases the solubility, which is a little bit a stretch that I'm making here, but also understanding the cluster formation in the solution. And when we are saying that when we are forming these large clusters, of course, they are going to affect the transport properties. So because we were comparing several different chemical classes, we came up with a metric we call it P overlap, which is the probability of distribution of diffusion coefficient between different species. So here the x-axis is the overlap of distribution of diffusion coefficient between lithium and polysulfides, and the color code is for lithium and solvent. Okay. One thing to note here is that there is an exponential decay in lithium diffusivity as the lithium polysulfide overlap increases, which kind of makes sense because you're forming these large clusters and they can suppress the the diffusivity of ionic species. We also noticed that with this analysis, we were able to categorize these 16 different chemical classes into 4 groups, which are shown here by the boundary colors. So with green, orange, yellow, and red. And these are the chemical classes which show similar behavior depending on this probability of overlap of diffusion coefficients. So I'll show an example of group A, which are these yellow boundary over layer, where we see high P overlap for lithium and polysulfide as well as for lithium and solvent. These are the chemical classes which contains phosphate, phosphide, sulfonamide, sulfones, and sulfoxide containing electrolytes. And if we zoom into one of the solvents, TMT, which is a sulfonamide solvent, we can see that there is a significant overlap in the diffusivity of lithium, polysulfide, and solvent. And because of the high viscosity of the solvent, which is one of the key metric, that overall results in a collective diffusion of these clusters in the solution and increases the viscosity of this electrolyte solution. All right, so based on this analysis, we categorize these 16 different chemical classes into 4 groups based on what type of different structures we are forming, the solubility of polysulfide, diffusion, viscosity, and ionic conductivity. We were primarily interested in solvents which can give us low solubility of polysulfide. So that's group 2, which includes fluorinated, non-polar, and silane solvent. Although they give very low ionic conductivity, but that can be compensated by the co-solvent that we are using here. Okay, so the next step, we further dig deep into one of the chemical classes, the fluorinated solvents, and we prepared an initial library of around 5,000 fluorinated solvents, screened them down to 1250 solvents based on the similarity measure index with the solvents which have already been tested in the literature. So out of 1250, 14 solvents have been tested in the literature so far, and we employed basically a bunch of different calculations with several different properties to systematically down-select them. This was a industry-funded project, so they came up with this matrix, and they wanted an electrolyte which can have viscosity of less than 2 centipoise and ionic conductivity of greater than 5 millisiemens per centimeter, and a certain cell cycle life and lithium efficiency. So we were chasing these metrics in this work. And so this is the design of experiments where we had a bunch of derived properties, properties from COSMO-RS, DFT, and MD simulations. And every property has a metric of either being high, low, or intermediate. The design space we are targeting is this, which is very difficult to achieve, where we are trying to increase the solubility of the lithium salts and simultaneously decrease the solubility of lithium polysulfide species. Again, there are many different polysulfide species. Okay. So I compressed down the results of all the thousands of solvents in this one slide. So from 1250, based on very detailed analysis of quantitative metric of different properties, we screened down to 18 fluorinated solvents. For these 18 solvents, we then did MD simulations for an electrolyte that mimics the composition of an actual battery electrolyte. So we have the salt, we have lithium polysulfide, we have additive, and we have a binary solvent mixture. Okay. The FLSN are the newly proposed 18 fluorinated solvents, and we compared the performance of these fluorinated solvents with reference systems, which are the state-of-the-art solvent mixture used in the literature, which is the ether solvent mixture, and DOL-TTE is the state-of-the-art fluorinated solvent mixture. Okay, so looking at the cluster analysis for the first and the second solvation shell, FLS0 to FLS18 are the newly proposed fluorinated system, and we compared the performance with DME and TTE. And you can see here that all the fluorinated system have higher tendency to form larger clusters, both in the first and the second solvation shell. Which tells us that they can significantly suppress lithium polysulfide solubility. That's what we were targeting. Among these 18, unfortunately, only 2 were commercially available. So we dig down deep into these 2 solvents and tested binary and tertiary solvent mixtures. So here you're looking at the experimental viscosity and ionic conductivity results in comparison with what we got from simulations. So first of all, this, I think with this very vanilla flavor, like all atom force field MD simulations, the predictions to me looks great because I have seen 50% error bars in viscosity calculations when we do all atom MD simulations. So overall, for newly proposed electrolytes, these results seem acceptable to me. What we found is for the proposed electrolyte systems, the ionic conductivity and viscosity actually surpasses the state-of-the-art electrolyte mixture which is used in the literature, which is DOL-TTE and DOL-DME. So we did all these bulk simulations, and the bulk simulation results look great. And let's see how the actual electrochemical performance of a coin cell look like. So for among 2 solvents, for one of the solvents, actually the capacity retention and Coulombic efficiency were really good and comparable to the state-of-the-art systems. For the other electrolyte, it performed fairly poorly because it didn't dissolve the additive in the solution. That's again a factor we did not consider in our the whole process. So again, when we are looking at when we're talking about electrolytes, and we saw a lot of good talks on the interfaces. When you find a new electrolyte, put it in a battery, it has to be compatible with the separator, with the anode, with the cathode, and we need to do all these different scale of simulations. So currently, what we are working on is this workflow in MISPR, which we developed, but it's not public. It's not out there on the website yet. Where you can start with the molecular species and the solid structure and composition and box size. It gives you the force field. Those are the only required things for this workflow. Come up with the force field definition, slab addition, data file, MD recipe, and then we'll do all the MD analysis. And then we are doing again the cluster analysis, a similar approach we had for the NMR flow near the interface to extract the stable structures and then feed them back to DFT and AIMD simulations. All right, this is just a snapshot of the model electrode. Right now, this is at a very preliminary stage where we are using solid charges at the interface, but we are in the process of continuously developing it and looking forward to any suggestions on how we can model it further. One of the problems we faced was people were not looking into additives, so we are also expanding the chemical space of other chemical classes. We are looking into a larger chemical space of ethers, sulfonamides, and adopting a very similar approach with getting a lot of screening these electrolyte based on properties computed, electronic properties from DFT, and thermodynamic properties computed from COSMOS calculations, and then screen down to smaller pool of candidates for more detailed MD simulations. All right, I think I have a little bit more time, so I'll talk about the last part of this talk, which is on using and developing machine learning models for predicting electrolyte properties. And in this architecture, on the left we start with the SMILE strings of salts and solvents, convert them into molecular graph, which passes through a layer of GCN blocks, and then these GCN blocks extract the atomistic features. We supplement them with handcrafted features as well, depending on the situation. And then, sorry, I think I have one thing missing here. And then, get the the graph representation. I had the molar percentage here, which is then scaled based on the molar percentage, and then passed through a multi-layer perceptron to predict a certain property. So we tested this architecture for a very small database which was available in the literature published in this PNAS paper, which consists of only 150 electrolytes with 54 solvents and 17 salts. And this data set has the experimental Coulombic efficiency for lithium copper cell. So here are the results. Don't look very nice, and they're not published also for the same reason. So we compared the performance of the proposed GCN model with linear regression and random forest. So here you are looking at the observed Coulombic efficiency and the predicted Coulombic efficiency, and the residual errors here. So overall, the linear regression and random forest behave somewhat similar for the training and test data set. There's a lot of deviation for the test data set. Compared to that, the proposed GCN model did a slightly better job for both the training and the test data set. But there were several, this is a very recent work, and there are several challenges we faced. This was a really small data set, very skewed toward higher Coulombic efficiency, because nobody wants to publish a bad data of poor Coulombic efficiency performance. So right now, we are trying to overcome some of the challenges by doing more feature engineering, as also coming up with a larger data set based using the LLM models. All right, so here's the model performance, not great, and that's, like I said, this is not even published, but what we were able to get out is some of the features which affects the Coulombic efficiency. So the top descriptors which affects the Coulombic efficiency are the solvent oxygen ratio and fluorine to oxygen ratio. So using this data and analysis, if we reduce the solvent oxygen ratio and increase the fluorine to oxygen ratio, that can improve the Coulombic efficiency. And we further looked into the effect of molecular features on several properties. So here we had a slightly larger data set of few thousand fluorinated solvents, and we saw that the features, and this is a very small list, we tested hundreds of features here, and we found that in case of fluorinated solvents, the degree of fluorination and proximity of fluorine to oxygen atom are the top descriptors which affect the ionization potential and properties like binding energy. And here you can see the effect of fluorination degree. Interestingly, these features are missing when you get the generic features from RDKit or moderate, which tells us that we may need a human intervention and supplement the handcrafted feature to kind of increase the accuracy of predictions. All right, so most of the work that I presented today was published as an open source database, the lithium sulfur battery work as COMBAT, which consists both the DFT computed electronic and thermodynamic properties, as well as the MD computed structural and transport properties. And at the end, I would like to just give you a brief demo of the MISPR website. We tried to make it a more well-documented website, but we are welcome to any suggestions. So we try to make it such that it's easier for anybody to use. It gives you the overview of the website, all the dependencies that we are using, how to install it. Again, it's as simple as pip install MISPR. You can also see all the prerequisite, and you can install it in virtual environment as well. We are using several base libraries from the material science community, so we have our own forked versions for that needs to be installed. It tells you how to set up your own database, how to run workflows. We have several workflows, but the users can also make their own customized workflows. So we provide some information about the basics of workflows and what it means to, let's say have a fire task. So we are using Firework package for workflow management here. As I mentioned, currently we have DFT-based workflows, MD workflows, and hybrid workflows, but anybody can, can use some of the basic utilities programs and can develop their own workflows. If you're interested, I would suggest to get started with this Code Ocean capsule, which we use to kind of conduct workshops for high school students to use MISPR to run DFT and MD simulations. And they have the Jupyter notebooks with all the code implemented already, which is, I think, one of the easiest way to get started with MISPR, and also the NMR tutorial. So the entire NMR workflow that I presented today can be accessed using these Code Ocean capsules. So hopefully I was able to give you some idea of how we are using this framework to run simulations in a high throughput manner and design some electrolyte components. I would like to acknowledge the funding from LG, Stony, Brook, NSF, and Institute of Advanced Computational Science, and experimental collaborations from PNNL and Purdue University. So thank you so much for your attention, and I would be happy to answer any questions.